Okay, so everything I'm going to talk about is the fruits of it's been over 10 years labour. And so this photograph was taken 8 years ago when we were here in this city, the four of us, at the International Centre for Mathematical Sciences in its previous building, which was a very beautiful old church. And like many old buildings, it was very difficult to keep in good order. It leaked, it was cold. So they built this rather excellent building instead. I put that photograph up, one, because I'm very fond of it, but secondly, because I think I'm going to use it to establish a theorem at the end of my talk. Okay, so again, the pointer doesn't work. Okay. So very slow beginning. Set up some notation. By inclination, my background is in economics.
It was a matter of turning it on.
Turning it on,
So
right?
now that we have done that, it should work.
So my background is in quantum probabilities, complex numbers, big infinite dimensional spaces, and very intricate arguments, where you can't really do anything other than argue from axioms and work very hard to establish inequalities. And many of you will be familiar with that. And then, say about 10 years ago, I had the opportunity to go to a conference, and I discovered that people were doing interesting things with matrices, which had actual numbers in. And you could even ask interesting questions for 3x3 matrices that people didn't know the answers to. So I thought this was an interesting opportunity to expand my horizons. And so I started working on problems like this. And the first thing that you can say is that if you come from a background working with Hilbert spaces, say you think of matrices as representing linear transformations, and then there's a sensible way to compose them. And that corresponds to the matrix multiplication, the matrix product that we all know and have been familiar with for many, many years. But of course, there's the obvious way of composing matrices. If you just think of them as arrays of numbers, then why shouldn't you multiply them entry by entry? Okay. Well, if you're thinking of them as representing linear transformations, that doesn't make a lot of sense, but there may be another way of thinking about them when this is a sensible thing to do. There is also a quotation attributed to a famous mathematician, but I couldn't look out which one it is. But every good definition should lead to a theorem. Okay? And I think the Hadamard product is a good example of this. Okay, so one thing you can do, one thing you should do, I would say, with a matrix is think about the associated quadratic form. It tells you lots of very interesting things. It's the route. It's the easy route in an undergraduate course to proving the spectral theorem. So here's the quadratic form associated to my matrix. So I multiply on the left and the right by vector and its conjugate transpose. And if the values that form takes are always non-negative, then we call it positive semi-definite. If they're strictly positive, then we call it positive definite. All very straightforward. The nice fact is that you can do various operations to your collection of positive semi-definite matrices in particular, and you stay within that set. In fact, it's a closed cone. Because I still have a great fondness for analysis, I like the fact that I have a closed cone because it takes limits. So you immediately get some really nice consequences from positive semi-definiteness. First of all, it's really easy to see that your matrix has to be symmetric. And then with the well-known polarization trick, it's easy to show that your matrix has to be emission has to be equal to its conjugate transpose. Okay, I'm including this only because there are lots of papers which talk about emission, complex emission positive semi-definite matrices, and they're just padding out their paper with a few extra words. Okay, so this always sets my teeth on edge. You might like it, you might prefer it, but it's not necessary. Some other things we know. So as soon as we realize that all our positive semi-definite matrices have to be emission, then we can use the spectral theorem, we can diagonalize them, and it's immediate that all those eigenvalues have to be non-negative. Well, that also gives us this rather nice decomposition as a square. So once we have our diagonal matrix, we can take the square roots of these numbers because they're non-negative, and so we have a square root. So, and the reason I'm doing this is because I want to collect all these together into again, a very simple theorem. There's nothing here that's sort of beyond maybe second year undergraduate linear algebra, but it points to a nice interaction of ideas. Oops. So the idea of quadratic forms, the idea of being Hermitian, the spectrum, diagonalization, spectral theorem, spectral decomposition, and writing something positive as product of this form. And all these have really, really powerful generalizations into various directions. This is the definition of positivity in C-star algebras. For example, the spectral theorem becomes an enormously powerful object once you go into infinite dimensions, etc., etc. So there's lots of really nice mathematics reflected in basic structure of positive semi-definite matrices. And then we come back to our Hadamard product, and we recall this maxim that every good definition leads to a theorem. Has anybody got any idea who did say that? Because the name of Arnold has floated into my mind, but might be. Has anybody heard it before? Or have I dreamt it? Yeah, people have heard it. Okay. And I think this is quite surprising. When I was first told it, I was surprised by it. The Hadamard product preserves the property of being positive semi-definite. And there are two ways of proving it. And one, the second one uses essentially a spectral decomposition and a very simple formula for the product in this case. So this is sort of easy but boring. And this is a sort of unmotivated trick, which is quite a nice way of doing it. You can write for the quadratic form corresponding to the Hadamard product as trace of the product of four matrices, and this you just have to be inspired and write this down. And then once you've done this, you use the fact that if A is positive semi-definite, then so is its transpose, and therefore we have a square root. And then you use the tracial property to move one of those square roots to the other side, and then you have something which is manifestly positive semi-definite, because you've got your positive semi-definite matrix B and you're conjugating it on both sides, and so that's going to preserve the spectrum, so the trace is going to be non-negative. Okay. So this is the one I like, but the drawback is I have no idea how you would motivate this identity if you didn't already know it. I've got a long train journey. I could possibly find that in 8 hours, maybe between Edinburgh and my hometown.
A short proof along these lines you can find in Christian Berg's book, Elementary, with sums without motivation needed.
Okay, very good.
He just calls that Schur product, not Hadamard product.
Right. So and you see the different usage. Schur's getting his name in for the theorem, so I thought Hadamard could have his name in for the product. Oops. So we then come to the immediate observation that okay, so if we've got the Schur product theorem, the Hadamard product preserved being positive semi-definite, so that means that Hadamard powers of positive semi-definite matrices will be positive semi-definite. And then we have our cone property. So we can multiply by any non-negative constant, and then we can add things up. Because we've got a closed cone, as long as we've got convergence, we can add up many times as we like. But another way of thinking of this series is it's precisely the matrix we get by applying the function, the holomorphic function with the same coefficients to the individual entries of our matrix. So this is where we start to see the idea of applying preservers entrywise turns up as a very natural idea as a consequence of how far can we push, or how one direction we can push the short product theorem. Yeah. So it's a pretty immediate observation that you have a holomorphic function of this form where the chlorine coefficients are non-negative, then as long as the entries of your matrix are such that everything's well defined, applying that function entrywise to your matrix, the property of being positive semi-definite. So that's almost obvious, and it clearly took no more than 14 years for people to realize this, because Collier and Shago then asked, is this all you can do? In other words, are the absolutely monotonic functions precisely the functions that preserve being positive semi-definite for square matrices of arbitrary size? So that was 1925. And the answer to this problem, as we all know, was discovered by Schoenberg, but it was really a byproduct of a completely different question. Well, maybe not a completely different question, but a question which is not obviously related. So, little interlude. So, round about that time, sort of 1930s, there was a lot of interest in isometric embeddings into different forms of space. So here's a theorem which Schoenberg obtained the definitive version after Frechet and Menger. Suppose you have a metric space, so set X with a metric row, and have n plus 1 points, x0 up to xn. Then you can embed these isometrically into Euclidean space. Moreover, you can specify how the size of the dimension you need by looking at the following matrix. So you take your initial point, and then the ij entry of the matrix, the distance from that initial point to xi squared, plus the distance from the initial point to xj squared, then minus the distance between xi and xj squared. You look at this matrix, and if it's positive semi-definite, then you can do your Euclidean embedding, and moreover, the rank of that matrix tells you the minimum dimension. Yeah.
What does embedding isometrically mean?
Sorry?
What is isometric embedding?
Keeps distances.
So the distance between points is preserved by the map. So you've got a distance row.
Okay.
In your metric space, and then you've got the natural Euclidean distance on RD. We're equipping that with that. So isometric is in that sense. So this is quite interesting, because if you're interested in isometric embedding problems, then you start realizing that actually knowing about positive semi-definite matrices is something that you might want to do. And then, of course, tends to infinite dimensions to at least the separable case in this way. Okay. And this was what Schoenberg was interested in. And of course, after you've done Euclidean space, which is the sort of zero curvature case, what do you do next? In the positive curvature case, you do embedding into the sphere. So this was where Schoenberg went next. So let's just fix some notation. So we take the usual representation of the d-1 dimensional sphere in RD. And the distance we want is the geodesic distance, which again, we all know what it is, but actually the formula for it is incredibly straightforward. And then again, Schoenberg obtained this embedding theorem, similar to before. This time we don't need to single out a particular point. So I've got n points x1 up to xn. And then again, we can embed them into some sphere of sufficiently high dimension. Well, firstly, arc cos, the inverse cosine function, is only going to give values up to pi. We better not have distances when you go to pi. So if they are, scale your metric, make this work. But the important thing is then when you apply cosine function to your distance matrix, again, what you get is semi-definite. Again, the rank tells you the minimum dimension required in order to do that. So again, this is a very nice result of Schoenberg. And then he obtained the following theorem, his 1942 paper, essentially considering these spherical embeddings. Okay. So his hypotheses were you have a function on the closed interval from -1 to 1, real valued, that is continuous and preserves the positive semi-definite property for matrices to which you can apply this function, and they can be of arbitrary size, of course they've got to be square, then necessarily the function you obtain has to be absolutely monotonic, has this power series representation on the whole of the interval, coefficients are all non-negative. So that was Schoenberg's result. And so he's therefore almost solved the Sago result. He specified continuity, but 17 years later, Rudin showed that actually continuity isn't required.
Be precise, only on open -1.
For Rudin's case,
For Rudin's
yes.
case, so
I'm
then-
going to be extremely imprecise about various technical details because they've been written down and published. So
Because-
I really want to know.
Because the fact that continuity is required in that case was proved by someone in the audience with Christensen.
I will move on swiftly. Of course, I knew that.
Paul is here, so.
Move on swiftly. Okay, so the natural question to ask, one natural question to ask after the situation is what happens if we drop the of any size requirement. There are some very nice proofs of this result that sort of characterize the behavior up to the sort of remainder term in order n, and then as n gets large, the remainders have to vanish and you recover the density. And that's very imprecise, but yes.
Question concerning theorem 6 and theorem 7.
Yes.
You say that the continuity is not needed, but the two
I'm cheating.
discontinuous limit points of the monomials,
Yes.
they would be the same.
So you are absolutely right, and Apurva has picked me up on that. So I have, by sleight of hand, I have changed the domain between theorem 6 and theorem 7. So you're absolutely right, and I should know better because I have read your paper, and I very much like the proof. So the proof that we're talking about here is very much a Choquet theory extreme points proof. It's a very beautiful way of proving it. And so the remainder idea is you get a clearer and clearer view of the extreme points as you increase the size, and the only ones you end up with what rule in for the monomials. Okay. I normally give this talk for a more general audience. Okay. So we then come to the question, what can you say about preservers for fixed size? And as Sujit said in his talk earlier, the 2x2 case is solved. Again, if you take the right domain, so pass it over proved in 1979 that 2x2 preservers of matrices with positive entries, positive semi-definite matrices with positive entries, are precisely characterized by the following three conditions. Function has to take negative values, has to be non-decreasing, and we've seen the 2x2 determinant argument which shows that, and moreover satisfies this condition multiplicative midpoint convexity. This isn't, yes it is, yeah, multiplicative midpoint convexity, which is the following form. So if you're multiplying the midpoint, corresponds to taking the square root. So we have this identity holding for all x and y in the domain of X. And then in particular, continuity follows automatically from. So that's the second complete characterization when n equals 2. We already said n equals 1 is very easy, and n equals 3. I don't think there's been much progress on.
Polite way of putting it.
So what can you say? Well, Roger Horn in 1969 published the following result, which gives partial information. So if your function again on the positive semi-axis is continuous, now we're assuming that, and preserves d by d positive semi-definite matrices, d being at least 3, then okay, so this first condition is not very interesting until d at least 4, but you have d minus 3 times continuous differentiability, and the derivatives that you obtain are non-negative on the domain of F. If you happen to know for some other reason that you can differentiate your function a little more, d minus 1 times, then actually that non-negativity condition carries through for those derivatives as well.
In this case, one would assume that one would believe that the function is in fact d minus 1 increasing, because if you have it for all these derivatives,
Right.
so it's
Yes.
probably this does not depend on the last condition that it is d minus 1 times differentiable. I suppose that
So you think this could be weakened?
So the-
slightly?
I could
Yes.
imagine this.
So the point is what it was also said, which Alex has skipped here, is that the d minus third derivative is convex. In condition 2 above,
It's not written there, but
it's not,
yeah,
but that derivative is
yeah.
also convex. So
Yes,
that
of course.
in that sense, it is increasing.
I mean, we had this discussion with how you could just say that it's d minus 1 differentiable in the weak sense,
The weeks.
because
Mhm.
it's a Sobolev derivative, and then
Yeah.
distributional, then you're settled.
Yes, thank you. Yes. So another direction you can go in, and I'm not going to talk about this systematically in this talk, is to say, actually, how small does my test set need to be? So I don't really need that positive semi-definiteness is preserved for semi-definite matrices. I can work with a much smaller set, and these individuals showed that actually you can get away with this set of matrices of rank most 2. So it suffices to verify the matrices of these form, in particular function f, have their positive semi-definite preserved, and the conclusion is follow. So you can have a very small test set. I don't think I'm going to go into that much further if we have those. Okay. So you can push this idea a little bit further. So now let us assume that our function is defined on a disk, complex disk centered the origin, positive radius. It's takes real values. That can't be right. takes real values for
Oh, that should be,
complex value, just. What do I want to say there? But that's very nonsense.
it should be C probably.
Yeah, I think it takes real values on the real axis.
Yeah.
I think that's the condition I want, so apologies for that error. Okay. Again, suppose it's a preserver, positive semi-definiteness, so C take values in this interval.
No, Alex, you wanted the coefficients to be real of F.
Yes, I do. I do.
But
want
that's
to-
what you
I
wanted.
want it to be a real, yeah, that's all right. Which is the same mistake.
Yeah, they will differentiate it. So, okay, yeah, sure.
So we just need to check with rank 1 matrices. Then actually, first D non-zero Maclaurin coefficients are strictly positive. And of course, if it doesn't have, that's assuming that it has. Okay. And the proof is very easy, so I've included it. So let's suppose the first D non-zero coefficients, the first one happens at order n1, last one at order nd. Okay. We just take the test vector with distinct entries, distinct positive entries. We've got the generalized van der Monde matrix that we've had mentioned previously. In fact, it's a nice one because it's one with integer powers, so it's much easier to see that these are convertible than the case where the indices are real. So the columns are linearly independent. Yeah. So they give us, so we can find a dual set for the space these span. Okay. Let's call them V1 up to VD. Okay. And then we take our function f right to a small enough multiple of our rank 1 matrix corresponding to U, and then evaluate at the corresponding quadratic form at the vector VI, and we get a normalization. Now here, if you just work this through, then you get the ith non-zero Maclaurin coefficient plus some higher order terms, which are going to vanish as your small epsilon tends to 0. But, so it's a nice, easy.
That notation, what is the U to the circle NJ?
Sorry,
Ah.
sorry. So this is the Hadamard product again. This is the this is, sorry.
Hadamard product of what and what?
Sorry, so U is a vector, column vector U1 up to UV, and this is the vector U circle N1, where I've got U1 to the N1, U2 to the N1, and so on up to UD to
Your Entrywise.
so it's the entrywise power. Yeah, yeah. Sorry.
Hadamard product with itself. Hadamard product with itself. many.
Yeah.
So
Strictly positive. Strictly positive.
because we've assumed they're non-zero. It's non-zero, it's non-negative, so it's got to be strictly positive. Good question. Okay.
Half an hour.
Right. So a lot more hard work. We established, so it's published in 2016. I think we got this sometime in 2015.
And we started it in.
We started in
when we first
2014.
met.
So we said, okay, this problem's a hard one, but perturbation is always a good idea. So what happens if we take a polynomial preserver and we perturb it by something small? And the question we had in the back of our minds is, okay, so if all these, if Ci, these coefficients, if these are all non-negative, then this will be a preserver. But maybe we can find some negative C prime so that we can show this thing still preserves matrices of fixed size. So that was the idea. And yeah, we managed to come up with a big characterization. So there are some points of interest here. So firstly, we have a fixed radius, and we have to fix a radius. Okay, so the first hypothesis is that this polynomial preserves positive semi-definiteness for d by d apply a closed disk. Second hypothesis, well, one way of ensuring this happens is just to make sure that all of these coefficients are non-negative. Alternatively, these coefficients are strictly positive. They're going to have to be strictly positive by the result we just saw. Okay. The first D non-vanishing ones have got to be strictly positive. And this term can be negative. We've got a precise bound on just how negative it can be given by this expression, which we see depends on these coefficients and on radius of the disk. So in particular, if you let the radius of the disk get arbitrarily large, this tends to infinity, this bound to tend to 0, and you don't get anything new. So we're talking about preservers not just of fixed size, but with entries of a fixed magnitude as well, no greater than a fixed magnitude. Okay. And it actually, the third hypothesis is actually, it turns out, to be sufficient to work with rank at most 1, basically with entries, with positive entries. Okay. So I'm not going to completely explain where this comes from, but I'm going to hint about where it comes from. Okay. And what I'm going to talk about here is a little bit anachronistic. It isn't quite how we originally proved the result. So the first thing to do is to rewrite things a little bit. So here's our setup. So the interesting case is where all these coefficients, C0 up to CD minus 1, they're all positive, C prime is negative. And then a little bit of rewriting means that we can fix our attention on this polynomial in X, which is transformed like T. And our question becomes, what is the smallest positive D, I should say? Is positive and C prime is negative, such that this polynomial preserves positivity on this set. Okay. And there is a really nice trick in a paper of Paul and Fitzgerald, which allows us to proceed, if you have the rank 1 case, to proceed by induction going up ranks. It's a really nice argument, which I haven't got time to go through here. But the fact that we can focus on the rank 1 case is very good news. Can I turn this off again? Yes. Okay, so let's look at the rank 1 situation. Rank 1 situation boils down to the following situation with that polynomial PT as on the previous slide. The matrix obtained by applying that polynomial entry-wise to the rank 1 matrix corresponding to a vector U, positive with distinct coordinates. This is positive semi-definite, and only if this determinant is non-negative. And then here, now that T has to be at least this quantity, where the ratio of squares of certain polynomials, shear polynomials, coefficients, the non-perturbed coefficients here as well. So this is a calculation essentially of this determinant translates to this inequality. So you then have to ask yourself, with the constraints of the theorem, how big can we make this expression? And it turns out, well, so it turns out it's maximized when all the coordinates of U are equal. And then essentially you're in the situation of wanting to know this quantity. Yeah, and this corresponds to the final dimension formula to get this expression of Random-Mondane determinants. If you work it all through, this is where you have the squares. This is where our squares of binomial coefficients come from. And if I remember correctly, and our Google will correct me if I'm wrong, we had quite a complicated argument to get the maximum figures essentially of this.
Well,
But-
not in our case, but yeah.
Okay, but there is a very nice result about ratios of sure polynomials, which gives what we need, which is this one. So if the collections of non-negative integers specifying your sure polynomial satisfy a certain order property, then the ratio of them is a non-decreasing function in each coordinate. This is very nice, and I think there's actually quite a bit of mileage at looking at analytical properties of the algebraic objects, which are sure polynomials. So putting all this together, we get our theorem, which shows that actually you can have fixed size preservers with, well, at least one negative coefficient. Which, and given the complexity of this result, I think it does show that the fixed dimension preserver problem is quite a difficult one. So let's leave it and let's turn to something else. So one natural place where positive semi-definite matrices appear, other than geometrical embedding problems, is when you look at moments of measures. If a measure with moments of all orders, then it has a corresponding Hankel matrix. Okay, so what can you say? Well, of course, there's a very nice relationship between the semi-Hankel matrix you get. That's positive semi-definite, if and only if the corresponding sequence is the moment sequence for a positive Borel measure. So if you have just classified preservers of positive semi-definite matrices, then you might naturally think of Hankel matrices and say, okay, can we classify the preservers of Hankel matrices? Or in other words, can we classify the preservers of moment sequences? And this is what we turned up to do in Edinburgh in 2016. And that can't be right. We started working on this 2016, didn't we?
Got published in 22.
Got published in 22, yeah. So we have to wait a little while for it. Okay, so this is the result. This is the first result. So if you look at functions that map a set of moment sequences of measures with support -1, then actually you get the Schoenberg class of absolutely monotonic functions. Now, Barlow, when he was here on Tuesday, this is not his words, so this is my interpretation. I'm not putting words in his mouth, but said a lot of these preserver results are quite negative because you just keep getting the same class, and that's a bit dull. I think that's perhaps a slightly harsh interpretation of what he said, but we were quite pleased that if you change this restriction, you can actually get something a little bit different. So suppose instead the measures supported on the interval 0, 1, so no mass to the left of the origin, then you get something slightly different you can have a jump at the origin. Okay. So for x positive, you have exactly this representation, but C0 does not actually have to be the value of the function 0. This has to be non-negative. So function has to be non-negative at 0, but C0 can be, you can get the next 0 there. You can have a jump. And then if you make things a little, slacken things up a little bit further, look at things that are going on right to the left of the origin. So now measures supported on the interval from -1, 0. You map into the set of moment sequences of measures supported anywhere on the semi-axis to the left of the origin. And actually, you can get again, you can get two different absolutely, you can get an absolutely monotonic function appearing with this reflected behavior. Okay, so that's some results for Hankel matrices. We've heard about results for wave frequency functions, so that's part of the Toeplitz case as well. Let me conclude, not quite, to the penultimate section with something about multivariable preservers. So again, we heard about this setup in Suter's talk earlier today, so he was nice and precise and gave some particular examples. I'm going to be abstract, but essentially, if we have a function depending on m real variables, mapping them into R, then we can apply it entry-wise, not just to one matrix, but to an m tuple of matrices in the natural way. So you just take the ijth entry of each of your m matrices, B1 up to Bm, and insert this into your function f. This will take your m tuple of n by n matrices to one n by n matrix, and now those positive semi-definiteness. So you have an m tuple of positive semi-definite matrices, well precise. When do they get mapped to positive semi-definite matrices? If and only if you have the natural extension of the Schoenberg type representation. It's an absolutely monotone function, if you like, so non-negative Florin coefficients, but here we have multi-indices. So x is x1 to xm, next to the alpha, alpha's an m tuple, so that's x1 to the alpha 1 up to xm to the alpha m. So it's just the natural way of writing this down. So this is a result of Fitzgerald, Micheli, and Pincus, and I apologize for not including here. Not been a guess. Okay, so I've included that because I want to talk about a different problem, which is interesting when you are dealing with m tuples. Again, you could say, well, this isn't particularly interesting. It's what you would guess. So there are lots of challenges in dealing with positive semi-definite matrices, and the fixed dimension case is very hard. But there is a sense in which seeing whether or not something is positive is easy, right? Easy to square. Right back to the beginning characterization. So harder is something a bit negative, right? And that's the question that we've recently turned our attention to. So I have to set up some notation. So S, N, K, I. Not really worried about the interval, but I is an interval. So the values of your matrix lie. N by n matrices. We're only interested in real symmetric matrices. And then we're going to look separately at those with no negative eigenvalues. So that's the class we've been interested in so far, the positive semi-definite ones. Those with exactly one negative eigenvalue, up to those with all eigenvalues negative. And of course, we're counting according to the multiplicity. And if I don't want to worry about the dimension, I want to take the arbitrary size, just take the units here, drop that part. Okay. So the first thing you might look at is the inertia of the matrix. Okay. So can I just do a poll of the audience that who knows what the inertia of a matrix is? Right. So we've got a very sniffy referee saying that this term inertia is a very strange term to use. I can tell them that it's generally used in the community. So first question you might ask is, what are the inertia preservers? So that is preserving the multiplicity, positive eigenvalues, the nullity of the matrix, and the multiplicity of negative eigenvalues. And the answer is there really aren't very many of them. Okay? If you preserve the inertia of all matrices of arbitrary size, then actually you have to just be a multiplication by a positive constant. So you can't, yeah, that's not quite right. Is that what you're? No, okay.
What is this theorem?
Sorry?
Where is this theorem? Like, where
Where
is
is
it
this
from?
theorem? It's on the archive.
Are you able?
Yeah, the forums. Went on the archive this year, I think.
Last year,
The most recent version went on this year.
most year.
Okay.
And I think this is a little bit surprising, actually. You can't sort of shuffle things around a bit other than just scaling everything. But actually, you get this, you get this rigidity, you get this positive homothesis appearing with less than asking preservation of inertia. In fact,
Again, are you keeping K fixed or is it?
I'm a little bit worried this statement isn't quite right.
Otherwise you would have all
So
matrices.
I don't want, that shouldn't be there, delete that. The Entrywise transform preserves the inertia of all matrices. So yeah, delete that, I think that's a slip. Here's where I do need a K. Okay. So suppose the Entrywise transform preserves a set of real symmetric matrices with precisely K negative eigenvalues. Okay. So that's less than preserving inertia. In principle, it can do anything it likes with the positive eigenvalues with the curve. Then actually, you've only got two possibilities. If you've got at least two negative eigenvalues, then you can only be a positive homothety. The other possibility is your map is just transforming all your matrices into a negative matrix with all entries equal and negative. What's that? There's one negative eigenvalue. But basically, as soon as you preserve the number of negative eigenvalues, you have to just be multiplication by a positive constant. So, okay, so maybe we're being a bit harsh here. Maybe we need to slacken things off a bit. Okay. So what about not increasing the number of negative eigenvalues? So let's foreclosure in some sense. Let's take SNK bar be all the n by n real symmetric matrices entries in I, which have no more than k negative eigenvalues. What happens there? Well, so here are three equivalent statements. Yeah. So we send the collection of matrices with no more than k negative eigenvalues to the collection with no more than L negative eigenvalues for arbitrary size. Or we send the collection of matrices with precisely k negative eigenvalues to the collection of matrices with no more than L negative eigenvalues for arbitrary size. Or we have two possibilities, either the constant function, not very interesting, but ability, or we get at least as many negative eigenvalues. L is at least k, and F is a linear function. And L is precisely k, this constant term, a linear into undergraduate geometry sense. If L and k are identical, then the constant term, straight line graph has to be.
By the way, the inertia preserver is perfectly fine with a fixed K. You
So
were,
it is, that
yeah,
was all right.
yeah, you were all right.
Okay,
Question,
please.
does condition one mean you just have a multiple of the all ones matrix? Yeah, multiple.
What the all one matrix would be admissible, yes.
What else is it?
So any,
It's a rank one matrix, basically, right?
no. Any matrix with no more than. Okay, negative eigenvalues.
No, the condition one of three.
Oh, sorry, condition 1 of 3. Oh, yes, sorry, yes,
Yeah.
you then you got, yeah, then essentially you get the multiple of the all ones matrix. Yeah. Yeah, K and L are positive. We've got at least one negative eigenvalue.
And what is condition two then?
Condition 2, so condition 1 is you start with the set of.
No,
matrices
which two?
with at least K negative ones, and then 2 is exactly K negative ones. So this set lives inside this set. So if 1 is true, then 2 will be true.
Thank you.
Now, so I've taken here K and L to be positive. We can also consider what happens when one of them, but not the other one, is 0. If they're both 0, then we're in the setting of the Schoenberg. We're talking about matrices with no more than no negative eigenvalues, going to matrices with no more than no negative eigenvalues, so positive semi-definite things. But what about the two edge cases? So our Entrywise transform sends matrices with no more than K negative eigenvalues into positive semi-definite matrices if and only if you end up with your ones matrix multiplied by some non-negative constants. Then going the other way, the Entrywise transform sends positive semi-definite matrices into matrices with no more than L negative eigenvalues if, again, we have the Schoenberg, but it's a bit of a cheat. It's positive semi-definite goes to positive semi-definite in here.
Except the constant terms, you're allowed
Except
to.
the constant, sorry, thank you very
One
much.
negative
Thank you
version.
for picking it up. Almost got stuff, but yes, you
Yeah.
can perturb by, again, an all ones matrix.
Yeah.
Okay, so Schoenberg slip. Oh, I've almost spun this out. Okay, so what do we get when we have tuples, preservers of tuples, in the situation that Sunik was talking about earlier? So we have some multi-indices, and K1 up to Km are non-negative integers. So let's arrange things so that all the zeros appear at the beginning if there are any. So M0 is the last 0 entry, this M2 K, then after that they're all at least ones. So if we've written them down the right way, we call them admissible. K max is just the biggest non-zero index we get, and to stop things breaking, if they're all 0, we just call it 1, and then we have the obvious product. So here is our theorem. So 1 and 2 is the similar, the weak case and the strict case, but exactly negative eigenvalues corresponding to K, or the weak version of that. And then here's our representation theorem. It's a mixture of the two things we've got previously. Okay. So for x1 up to xm, 0, okay, all the corresponding indices are zeros. So we're talking about positive semi-definite matrices. So for them, we can work with absolutely monotone functions. Everything will be okay. Then for the indices m0 plus 1 up to m, and the corresponding entries of k are at least 1, so our preservers are at best homotheticals of this form. Actually, we can have these together, everything will be fine. And finally, there's a slightly fiddly condition here. We have to have enough negative eigenvalues available to us in the range space for everything to work. So, okay, it's a combination of the two familiar classes of preservers we've already seen, but it is at least quite an interest. I mean, it's slightly complicated state, so I would hope it's a slightly interesting combination. Okay, so I'm going to finish there. And I'm going to finish with my theorem. So my theorem is that doing mathematics is good for you. But I think for 8 years later, we're looking pretty good. The vagaries of time. Okay.